Good afternoon. My name is Karina Figueroa, and I will talk about permutation-based algorithm improved by classes for similarity searching. This work is worked with Antonio Camarini Barrolas, Nora Reyes, and Rodrigo Paredes. The outline of this presentation is as follows. First, I will give you some introduction with motivation and basic concepts. Then I will talk about related work, and I will introduce our proposal. Finally, I will show some experimental results and conclusion of future work. Okay, similarity searching consists in retrieving the most similar objects to a query from a database. The similar or close objects are important for so many real applications, most of which are related to multimedia database where an exact search is useless. The similarity is defined with a distance function or a metric proposed by an expert on those fields and that considers a specific feature from data. The problem can be modeled as a metric space. This is a pair of universal objects and a distance function with these properties. In general metric spaces, the distance function, which is considered as a black box, is the only way to distinguish between objects, and usually the distance function is expensive to compute. Basically, there are two kinds of queries, range query and k-nearest neighbor. The first one, we need a query and a radius, and we need to find which elements are within that radius. And the second problem is uh, known k-nearest neighbor. Okay, first I will introduce the permutation-based algorithm. This is, we select a subset of the database and we call them permutants. Each element in the database compute the distance to all the permutants and sort each distance. And this sorted is considered as a permutant. As this order of this permutants is considered as a permutation of this set. This is the main idea. All those points are our database. We select some points and we call them permutants. Each element in the database computes the distance to the permutants and sort them by proximity. And this order is considered as our permutation. When a query is given, we compute the distance from the query to all the permutants, compute the query permutation, and finally, we compute the similarity between permutations in the database and against the query permutations. This is the idea. I have the query permutations. Permutant 4 is closer than permutant 1, 3, and 2. And notice that element U2 is closer to the query and the permutation is exactly the same as the query. And in the other hand, we have the other permutation here from element U1, and this is not similar to the query permutation, which is according to the main idea. Okay, our proposal is, in this case, we have two permutants, P1, the blue ones, and notice that element U2 is closest to the query. This is the U2 element, and this is number U1. And notice that query is closer to the permutant 1 than the permutant 2. The same for this element, but in the other hand, its closest element is 1. But in this case, this element U1 is closest to permutant 2 and then permutant 1. So in order to avoid this kind of problem, we propose to use set instead of one permutant. We call each set as a classes. Formally, we have a set of classes, which each class is a partition of the set of permutants, and each class has exactly m elements. So the new distance that I need to introduce is the upper D, which this distance compute the distance between an element U of the database and a class A of the set of the classes. And in this case, we need to compute all the distance to all the classes and sort these distances by proximity to U. But how to choose element in each classes? So we propose some heuristics. Random is select each element in each class by random way, or we can select first element and add the m-1 closest permutants, or we select one of element and select for each class to the m-1 farthest permutants, or we can select two mutual nearest neighbor and add closest element to this part. Or in the literature, in particular in make spaces, there is a technique which is a sparse selection, which is called SSS, and we can select each element in the class using this technique. So another definition that I need to introduce is the how to compute the upper D. We can compute the upper D minimum, which is the lowest minimum to all the L objects in the class, or D max, which is the greatest distance to all the objects in the class, or the average. This is the average of the distance to objects in the class, or a combination of average and minimum. This is AM, DAM. So in this case, we are showing an example. The blue ones are one class, the red one are a second class, and the third one is the third class. Notice that we have different permutation for each distance used. So our experimental results, we show that some real databases. In the first one, we have 40,000 elements, 20 dimensional vectors, and notice that in this case, our technique using 2 elements per class is reduce the number of distance needed to solve the problem. The other database used is a bigger one, which has 112,000 elements with dimensional feature vectors in 112 also features. In this case, notice that the line in red and the line in blue, in black, are the previous idea, the original idea, and using some parameters that you can find in the paper, we can reduce the work up to 40%. And the last one, this is a database with 10 million elements with 208 dimensional vectors. The name is Cohere database. And in this case, note that using the new distances, using SSS heuristic, and using 3 elements per class, we can reduce the distance to find the 20 nearest neighbor up to 80% of work that the original idea. As a conclusion, I can say that the original idea is to use classes of the permutants instead of single one in the permutation-based algorithm, and we introduce a new distance between classes and experiment with different way of selecting elements inside the classes. As a future work, we show how this technique works using different size of classes. Thank you so much.